Welcome to the deep dive. Today we're really wrestling with something fundamental, time itself.
That's right. We've got some fascinating source material you sent in, all pointing towards cutting-edge physics and this core question, what is time?
Exactly. And our mission today is to take these ideas, especially Einstein's concept of space-time, and see if we can make them, well, clearer.
Mm-hmm. Space-time. That's the bedrock here. You take the three dimensions of space we all know, width, length, depth, and you add a fourth dimension, time.
Okay, 4 dimensions total, but
Yeah.
here's the immediate problem, isn't it? If time is the fourth dimension, why can't I see it?
Ah, yes. The invisibility problem.
I mean, I see length, I see depth, but time, it feels completely different. Where is it? How does it hide?
Well, that apparent invisibility is precisely what splits the scientific community, according to our sources. It's a huge paradox.
So on one hand, we experience it constantly. We age, we remember, things happen in time. Seems pretty real.
Absolutely. Our daily experience screams that time is real. But then you have serious theoretical physicists who argue, based on their models, that time might be more of an illusion,
An illusion, like something our brains cook up.
or something that emerges from a deeper reality, not fundamental itself.
Mm.
It's a really profound debate. We feel it, but can we prove it exists fundamentally?
Wow. Okay, that's a big claim to just drop on us.
It is, which is why the sources really emphasize a certain mindset for this. They basically say, use your imagination, think deeply, but don't just swallow it whole.
Imagination is more important than knowledge. Wasn't that the quote?
Mm,
Especially for this kind of thing.
exactly that quote. So to help that imagination, the sources offer a really useful visual analogy.
Okay, I think we need it. Let's get into this idea of space-time being an invisible interweaving. How do we picture that?
Right, so picture a fish tank. Perfectly clean, clear glass, filled with perfectly clear, pure water.
Got it. Just water in a tank.
That water, that clear volume,
Mm-hmm.
that represents the three dimensions of space. It's simple.
Okay. Space is water.
Now, into that clear water, we add something else. Pure white salt, fine grains. And this salt represents the particles of time.
Particles of time. Interesting. So you pour in the salt.
And then you stir it really well until it's completely dissolved, perfectly uniform throughout the water.
Right, so now, looking at the tank, it still just looks like clear water. You can't see the salt anymore at all.
Precisely. But, it's not just water, it's salt water now. And that salt water is space-time.
Oh, okay. So space and time are combined, interwoven like salt dissolved in water.
Exactly. The salt particles, the time particles haven't disappeared. They've essentially transformed into an invisible property of the water, a time field.
A time field woven through all of space.
Every single point in that water now has this saltiness component. It's fundamentally changed, even though it looks the same. That saltiness is the invisible time dimension, permeating everything.
So that's why we don't see the fourth dimension. It's not like next door to space. It's in it, chemically bonded almost.
That's a good way to put it. It's an intrinsic property now. The saltiness is the hidden mechanism.
Okay, that actually helps. So if the whole universe is this 4D saltwater, this space-time, what happens when you put regular 3D stuff in it? Like us or a planet?
Good question. That's the next step in the analogy. Let's introduce matter.
How?
We take a clean, white sponge, something obviously 3D, with a clear shape and volume. Think of it as any object, like your hand or the earth.
Okay, a white sponge representing matter.
Now dip that sponge into the salt water into space-time. What happens immediately?
Well, the salt water rushes in, right? Fills up all the little holes and pores in the sponge.
Instantly. It seeps into every part of the sponge's internal structure. That movement, that absorption of the space-time salt water into the matter. That's the sources call matter's time.
Matter's time. So time isn't just around the object, it flows through it.
It becomes internal to it, woven into its very fabric, just like the salt water fills the sponge. But critically, look at the sponge now.
It's still just a white sponge. You see the 3D shape, but you don't see the water inside, and you certainly don't see the dissolved saltiness.
Exactly. Time is hidden inside the substance. It's not an external thing we observe easily.
Right.
It's an internal property, activated, you might say, by being within space-time.
It feels less like a dimension we travel along and more like we're soaking in it.
That's a very apt description based on this analogy. And this leads to a neat little thought experiment the sources mention.
Oh.
Imagine if the salt wasn't clear or white. Imagine if it was, say, gray salt.
Okay, gray salt.
Then the salt water would be gray, wouldn't it?
Yeah, the whole tank would look murky gray.
Right. And then what happens when you dip the white sponge in?
It would instantly turn gray as it soaked up the gray water.
There you go. If time had some easily measurable, visible property like color, then matter interacting with spacetime would change visibly. We'd see the effect of time permeating the object.
You'd see the grayness along with the 3D shape. But since the salt is invisible, the effect is hidden within the matter itself.
Precisely. Which brings us to a really mind-bending idea from the sources.
More mind-bending than invisible salt dimensions. Okay, I'm ready.
Well, it follows logically from the analogy, actually.
Go on.
If the sponge matter is obviously 3D,
With length, depth, yeah.
and the saltwater spacetime, including time, fills it completely in every one of those 3 dimensions,
Filling all the pores.
then shouldn't the saltiness, the time component itself, also be considered 3-dimensional, matching the space it fills?
Whoa, hang on. You're saying time isn't just one line forward, but it could have width and depth too, like space.
That's exactly what some cutting-edge theoretical physics research is exploring. The possibility of 3D time. 3 dimensions of time mirroring the 3 dimensions of space.
Hey, wait. Everything I've ever learned, Einstein included, treats time as the 4th dimension. Singular. Just one direction, forward. Why? Why simplify it if it might be 3D?
That's a crucial question. And the answer mainly comes down to practicality and, frankly, math.
Math. Okay.
Think about calculating something complex, like a planet's orbit or a rocket trajectory. To do that precisely, physicists usually focus on the object's center of mass, or its center of energy.
Right. You treat the whole huge planet as basically a single point for the big calculations.
Exactly. And for that single reference point, you only need to track its progression through one dimension of time forward. You don't need to worry about potential time variations within the planet itself for most large-scale calculations.
So modeling time as 1D makes the math vastly simpler, and it works for predicting orbits and stuff.
It works incredibly well for almost everything we can observe and measure directly. It's a fantastically effective simplification, a powerful tool.
Okay, it's a useful tool. But the analogy suggests the underlying reality, the salt water filling the whole sponge, might be more complex. It might be fundamentally 3D.
That's the hypothesis, that the 1D treatment is a simplification that captures the overall movement but maybe misses the internal temporal structure.
And does this connect to things like string theory? They're always talking about extra hidden dimensions, aren't they?
Absolutely. The search for a theory of everything, whether it's string theory or quantum gravity, often involves proposing extra dimensions beyond the 4 we perceive. And yes, some of those hidden dimensions could well be additional dimensions of time.
And having extra time dimensions might solve some physics problems.
Potentially, yes. Big problems, like maybe explaining why time seems to only move forward the arrow of time puzzle, or figuring out what happens inside a black hole where the 1D time model kind of breaks down mathematically. Understanding time's true dimensionality could be key.
So understanding time that feels like it must connect to gravity somehow. The sources kept linking them.
Directly connected. You can't understand gravity deeply without understanding space-time and therefore time.
How does the 1D versus 3D time idea change how we think about gravity?
Well, let's quickly recap Einstein's general relativity. The core idea, based on the sources, is that gravity isn't really a force pulling things.
Right, it's about the shape of space, or space-time.
Exactly. Mass and energy tell space-time how to curve. And the curvature of space-time tells mass and energy how to move. It's a relationship.
Like a heavy ball on a rubber sheet creates a dip, and marbles roll into the dip.
A classic analogy, yes. But remember, the sheet isn't just space. It's space-time. It's our saltwater fabric.
So a massive object, the sun doesn't just curve the water, it also curves the saltiness. It distorts time, too.
Precisely. Big masses cause what's called time dilation. They literally slow down the passage of time in their vicinity. The stronger the gravity, the slower time flows relative to somewhere with weaker gravity.
Well, that's real, not just theory.
Oh, absolutely real. Proven. We have to account for it every single day for GPS to work.
GPS? How?
The GPS satellites are orbiting high above Earth, where gravity is slightly weaker than it is down here on the surface.
Okay.
That means time on board the satellites is running just a tiny, tiny bit faster than time on your phone or GPS device.
Faster. Wow, how much faster?
We're talking nanoseconds, microseconds. But GPS relies on incredibly precise timing signals. If the system didn't constantly correct for that time difference, that relativistic time dilation, the positioning errors would build up so fast, the whole system would become useless within minutes.
So the fact that my map app knows where I am is direct proof that mass curves time. That's amazing.
It really is. It's a daily validation of Einstein's spacetime and the intimate link between mass, gravity, and the flow of time.
Which brings us back to the core challenge. If we could truly figure out if time is 1D or 3D or something else entirely, that sounds like the key to uniting gravity, the big stuff.
General relative.
And with the physics of the really small stuff,
Yeah.
quantum mechanics, that's the big prize, right? The theory of everything.
That is the ultimate goal for fundamental physics, yes. And understanding the true nature of time, that invisible saltiness, is almost certainly a critical piece of that puzzle.
What a journey. Okay, so let's recap. We started with Einstein's 4D spacetime, the basic idea.
Then we use that saltwater and sponge analogy to try and visualize why time might be invisible but still everywhere, inside matter itself.
Leading to that pretty radical idea from current research, maybe time has 3 dimensions, just like space.
And we saw how that connects directly to gravity through space-time curvature with real-world proof like time dilation affecting GPS.
It really puts time in a whole new light, or maybe puts the lack of light on time in perspective.
Nicely put. And just to echo the sources one last time, this is all meant to spark thought, to get you questioning. It's not about handing down final answers. Critical thinking is essential here.
Absolutely. So we'll leave you, as the sources did, with one final, really provocative question to mull over. It gets right to the heart of that gravity-time connection.
The question is this: does time affect gravity, or does gravity affect time? What is it, and how is it possible?